Today we'll be talking about how we look to make machine learning easy for engineers using a new low-code approach that really anchors on this idea of a declarative interface. What we'll do is walk through a setup on how this platform and interface really got started, anchoring on our open source project that really looks to make machine learning be accessible for every software engineer out there. And we'll go through a demo about how you'd be able to build models declaratively yourself and get started today. As a brief introduction, today you'll be hearing from myself. I'm Dev Rishi, the co-founder and chief product officer for Predabase, as well as Joffrey Angus, to give a brief, a machine learning engineer at Predabase. To give a brief introduction to both of us, my background was as a product manager across a number of different teams at Google, including Firebase, Google Research, and Vertex AI. I was also one of the first PMs for Kaggle, a data science and machine learning community that Google acquired in 2017. And over that series of time, saw a lot of different applications of trying to increase access to ML. Jeffrey was himself a software engineer at Google as well, and worked on a lot of machine learning projects, especially as part of Google Research. Both of us today now are at Predabase, which is a low-code ML platform built on top of Ludwig, an open source declarative machine learning framework that you'll be hearing a lot more about today. Now, to get started, here's an obligatory slide on how machine learning is starting to permeate every application's surface area of products. And it honestly is something that we've seen up close and personally. One of my co-founders, Piero, in a few years at Uber, found himself working on a series of machine learning applications to be able to improve the underlying Uber product, everywhere from automating customer support to working on fraud detection and recommender systems. The types of use cases were extremely diverse, and every few quarters there'd be a new project that they could work on in order to be able to improve Uber's top line. And personally, it does feel like every product team that I've worked on has had an item on their roadmap to improve something in their product with machine learning. And quarter after quarter, what I've noticed is that this ends up being punted out, usually because there's only a small number of people in the organization that know how. So while the engineering teams often may end up signing up for a machine learning task, it typically ends up getting moved out, either because they're blocked on some data science resourcing, or because they started an experimental project, but it never really gets to the point where it's production ready. And what we think is that there needs to be a technology shift that can start to put ML in more individuals' hands so that this can actually get broader access.
Hey Deb,
now,
we're not actually seeing the slides.
Oh, you're not? Okay, sorry. Let me, I see. Hopefully you're seeing them now. Great.
Yes.
No worries, you didn't miss anything too substantial on the initial slides, but I'm glad you're able to see them now. And so what we wanted to say is that, we believe that there's a technology shift required in order to be able to increase the amount of access to machine learning, but also recognize that, we've been discussing this idea of democratizing machine learning for quite some time. Starting all the way back in 2012, a little bit over a decade ago now, we started to see the early tweets of, can we put machine learning in the hands of students? Can we put machine learning in the hands of analysts? Can we put machine learning in the hands of engineers? And can we put it in the hands of more business users? And so this, I think, idea has been really, really popular, since the beginning of ML showing its promise. But what we want to do specifically today is take a look at it from the software engineering perspective and see how we can open up access to savvy developers. One of the first things that we need to recognize is that building an application to use machine learning is not a typical engineering task. In particular, there's layers of revealed complexity, and the deeper you get, the bigger the problem tends to actually be. So the first thing that I think any software engineer who dives into machine learning tasks realizes is that model training itself is a complex area, that it consists of a fragmented ecosystem of machine learning frameworks that they'll need to learn how to stitch together. This also often requires a certain level of expertise in terms of how to write either Python code or even lower level code for something like a PyTorch or TensorFlow. After you've finished your model training, then one of the key things about machine learning that makes it quite different from software engineering is that machine learning tends to be a very iterative journey before you can have your first results. And so in data science, we often say that your first model is never your last, which means that you need to spend anywhere between weeks to months iterating on your model to be able to get to a point at which you're happy with. This means a combination of being able to understand the best-in-class techniques for ML, as well as how to interpret the outputs of models, visualizations, and other statistics such that you could actually get to the result that you're looking for. And then finally, there's a class of questions around what to do once you have a model that you're happy with. Oftentimes, this means model deployment. And while this looks closer to the types of engineering tasks that most software engineers and developers spend time working on today, model serving and deployment is its own specialized series of infrastructure challenges, and often presents, a significant roadblock towards users that are able to get started with ML. And so in summary, what we see is that engineering teams tend to be roadblocked on machine learning for really three key reasons. The first is that there's just candidly a zoo of machine learning tools out there, a fragmented ecosystem that requires engineering teams to figure out how to stitch together a certain machine learning framework with a certain underlying infra for training, a certain model monitoring and experiment tracking tool, a different thing for serving, and many others for monitoring, for example. The second and perhaps most pervasive problem, and the one that we hear most commonly, is also about the limited machine learning expertise. The lack of a data science background might mean that strategies on how to get started with the first model or iterate on the next 7 can be really limited in terms of the number of engineers that actually can access it inside of an organization. And then, of course, infrastructure headaches mean that software engineers who could be spending time building a new fast feature into the product or working on other optimizations now need to spend time learning how to be a machine learning infrastructure engineer and spend lots of time maintaining that infra and then executing large-scale machine learning workloads. Now, luckily, we know that developers tend to be very smart, highly capable technical users. And so there must be a different way that we could actually look to simplify this problem by placing it in that specific audience's hands. And if we were to take a look at this and start to explore the broader area for inspiration, I think we could work backwards from other hard technical challenges that engineers have solved into making simpler tasks. And I think 2 examples we really like about that are how dbt made data engineering easy for analysts, and how something like Terraform makes managing infrastructure and cloud infra much easier for DevOps teams. So each of these technologies essentially allowed something that you took a little bit more specialized knowledge and put it in the hands of many, many more users across the organization. And I think it sort of begs the question of what is machine learning's equivalent of Terraform, as an example? How do we make machine learning easier or more accessible for engineers to be able to get started while supporting them for the depth that they might need in a complex task like ML? The nice thing is it turns out that some of the big tech companies have already started to look at this so that they could solve their own problems internally. This is a quote from a paper that Meta, formerly Facebook, posted about their internal machine learning platform called Looper. And what they reflected on when they were building Looper was that the system needed to accommodate software engineers without backgrounds in machine learning and provide mechanisms to optimize for many different product tools. And so as Meta took a look at this particular task, they actually came to a very similar conclusion of how to build and architect their ML platform as a couple of other leading technology companies. And what the top 10% of companies that really build and see high ROI for machine learning know that isn't really accessible to the broader enterprises today is to use what we call a declarative machine learning system. So the 3 internal ML platforms at these 3 tech companies, Apple, Looper, Apple, Meta, and Uber, all use what we call a declarative interface to machine learning. And today, combined, these internal ML platforms have consist of thousands of models and have processed billions of queries for inference across the 3 organizations. Now, I feel particularly close to this story as two of my co-founders at Predabase really built two of these systems directly at each of these organizations. And so Chris was one of the main authors for Overton at Apple, and Pira was one of the main authors of Ludwig while at Uber. And the key idea that they really faced was that they were inside massive organizations that had a high number of software engineers and had started to see a really high ROI to machine learning, but recognized that in order to be able to continue to realize that pace of innovation, they needed to put machine learning in the hands of all the developers that existed in that organization. So at this point, declarative machine learning, I think we might seem like a promising start, but a number of you might be wondering, what exactly is declarative ML? And let me do a brief introduction to what that actually is. And we can start with Ludwig, because Ludwig is the open source declarative machine learning framework that came out of Pira's work at Uber. And the key idea behind Ludwig is that you can start very simply, but get to all the depth that you would need inside a machine learning project by using a configuration-driven interface. So in this screenshot, what you can see is these 6 lines of configuration, just saying I want to use an input feature that is text, that is the description, and I want to output a category feature, which is intent. Just these 6 lines of configuration are all you need in order to be able to set up a state-of-the-art machine learning pipeline. And that state-of-the-art machine learning pipeline will pre-process your data, encode it using a series of the latest and greatest machine learning platforms, machine learning models that will do everything from handle everything from numerical, categorical, text, audio, image, and many other types of input features. It'll also handle post-processing as well as the full training loop that you normally need to use for your machine learning models. The great thing about this declarative approach is that it's also highly customizable. And later today, we're going to show you how you can take a very simple configuration like this and be able to really customize it and iterate to be able to get to your final model that you're excited about and ready to make the transition to in order to put into production. But the thing that I wanted to essentially introduce here is that declarative machine learning makes it very easy to allow a user to get started with ML while making sure that they persist the control over the parts of the pipeline that they want. And we see that this approach essentially has made machine learning easy for the many engineers that have started to use Ludwig across both tech companies as well as other projects. And the real advantage that we see is that instead of a zoo of frameworks, users now don't need to reinvent the wheel. They can just build state-of-the-art ML pipelines and a few lines of YAML configuration. Instead of needing deep expertise in machine learning, users can pick and choose the parts that they want to control and allow the pipelines to be automated, or the rest of the pipelines to be automated via the config. And instead of having to deal with massively complex infrastructure, software developers now can reduce the infrastructure of friction by getting things like distributed training and many other optimizations out of the box. What I'm going to do now is hand it over to my co-presenter, Jeffrey, who is a software engineer himself, and therefore will be able to really dive a lot deeper into what exactly are all of the benefits that we see from taking a declarative machine learning approach and how this can work in practice, including a live demo. So Jeffrey, I'll transition it over to you and let you take it away to be able to talk through the rest of the presentation.
Awesome. Sounds good. Thanks, Dev. Can you see my screen if I do something here on the side? Okay.
Yes, we can.
Okay, great. So thanks so much. I'm Jeff. I'm an engineer turned data scientist, and I'll be talking you through why I'm excited about declarative ML and why I dedicate my time and effort in building and maintaining Ludwig myself. So as Deb mentioned, we have these 3 points, and I'll be going through each of them individually throughout the course of the presentation. But first, let's talk about building your first ML model. So this can mean different things to different people, depending on your ML experience. For some of you, this could mean the first model for your project. For some of you, this could be your first model ever. Regardless, building your first model, especially if you're on a pure software development team with no ML support, can be quite challenging. You have to wrangle your data, write data loaders, implement or import some sort of model architecture, and wrap the whole thing in a training pipeline to ensure that the entire process logs, metrics, and saves your artifacts. Not to mention, you have to figure out how to get that model out of that pipeline and into production. This has been done 1,000 times probably tens of thousands of times in the past decade. And as the maintainers of Ludwig, we urge you not to reinvent the wheel. So in 6 lines of YAML, as Dev was mentioning, you can train your first deep learning model. And this is possible through a schema-driven design that dynamically creates ML models using the feature types specified in your configuration file. So here we have a nice animation that shows exactly what that means. So Ludwig uses a feature type abstraction to ensure that your data is correctly represented in the internals of your model. The feature types of your inputs include feature types from classical tabular ML, such as binary, category, and number features, as well as unstructured feature types that call for deep learning techniques, such as image, text, and audio features. All of these feature types are available to you through Ludwig, and you can compose them, mix and match them as you need in order to address your particular use case. This slide demonstrates some of the use cases found by Ludwig users. You can see that while the config remains under 10 lines of YAML, you are able to mix and match and do things for a massive variety of data sets, including the simple, such as tabular regression for housing price prediction, to the complex, such as visual question and answering, which takes a combination of image inputs and text inputs in the form of a question to generate text-based answers. Now, with this in mind, let's take a step back again into the imperative world. So let's imagine we're once again in this universe where you don't have Ludwig. Here, again, is that code you wrote to train your first model. And the good news is you've trained your first model, but the bad news is, as Dev said, your first model is rarely your last. There can be many reasons for this. You may have misunderstood something about your data. The model's performance in terms of accuracy or utilization and latency was not quite where you wanted to be, or simply that the underlying data assumptions that you had or business requirements changed while you were in the middle of your model development phase. In any case, the typical ML development workflow is highly iterative, and the assumption is that your first model acts as a baseline, and that each successive iteration is better than the last. However, in the imperative world, it's not uncommon that every subsequent improvement to a model requires a code change, which further lengthens the model development lifecycle. Fortunately, Ludwig allows you to control what you want and automate the rest. Here again is a running example of a Ludwig config object. As you know already, this config object dynamically generates a machine learning model architecture for training. However, there is a crucial intermediate step. If we consider our input feature, we see that we've only specified 3 lines, that it's an input feature, that it's a description, and it's of type text. However, behind the scenes, Ludwig renders this into a much larger config object. So between generating the model architecture and your 3 lines of YAML, Ludwig actually generates this piece of code. Ludwig comes built in with sensible defaults for every aspect of the config, guaranteeing that the minimal configuration produces a seamless model training experience for that first quick and dirty baseline that you need for your use case. This rendered config is saved as one of the artifacts of model training, so you get the nice property of always knowing what your model is made of, which differentiates this from traditional AutoML frameworks that you may have seen in the past. However, the real benefit of having so many defaults, as a software engineer might know, is that they can be overridden. So let's go ahead and consider a real-world example. This slide represents a large sort of block of code that actually is a full and complete example of a single model training pipeline in a low-code yet imperative deep learning framework. It's got all the bells and whistles required to achieve state-of-the-art performance on a classic natural language processing dataset, including making use of a Hugging Face pre-trained model, Albert, using a learning rate decay schedule with warm-up, and incorporating sort of those data loading techniques that you need in order to do this. In Ludwig, model iteration is much more simple and requires a lot less code. So with your 6 lines, you get your first model. But after that, we want to iterate, and we want to eventually get to the point where we can reproduce the results of that prior slide. So we may add 2 more lines of code, and now we're using this state-of-the-art text encoder, Albert. And then after we've trained that first model and realized that maybe our learning rate was set too high, and that we weren't getting that convergence that we needed, we can add 4 more lines of code. And now we are expertly tuning our model for best-in-class performance. So in these 13 lines of YAML, we are able to build out that high-performance model that we saw on the previous slide required hundreds of lines of code. So I think at this point, we've established that declarative ML can be a really powerful layer of abstraction to enable rapid baseline creation, model iteration, and generally just a quick way to realize value from your data. However, we have to ask ourselves, is it ready for prime time? Let's go back to our real world state-of-the-art example. So what I'd like to talk about now actually is if we take that code block and imagine it as part of a larger ecosystem of code, we can start thinking about what I like to call the ML infra iceberg. As Dev was mentioning earlier, ML is this sort of thing where the deeper you go, the deeper it gets. And this is certainly true, particularly as you scale your data and your models. So from the get-go, if you are training a small tabular regression data set or training a tree-based model, that bit of code that you wrote to train your model might be all the code you need to get it into production. But as your data set size grows and your model size grows, so for example, if you have a medium-sized text classification data set and you're starting to use embeddings in a neural network, maybe the infrastructure becomes more sophisticated. Maybe you need to use GPUs. As your data set gets bigger and your model gets bigger, maybe you need multiple GPUs spread across multiple nodes, and now you're having to do distributed data parallel GPU training. And if your data set grows and your model grows even more, maybe now your data set no longer fits into memory, and you have to do data set sharding and pipelined data loading. And so really, the model that you've built is really just the first step. And at some point, if your ML becomes sophisticated enough, a lot of your engineering time is actually just going to go into allowing your models to train efficiently and quickly. So this is all true and a hard pill to swallow, but ultimately, one thing to consider is that these optimizations, while tricky to implement, essential to get right, they're ultimately just boilerplate, which means that they can be generically applied to many ML pipelines. In Ludwig, we took this to heart and sort of consolidated it into the platform. And so with a few additional lines of YAML, we're able to integrate with technologies like Ray, Dask, and Horovod to get that best-in-class infrastructure. So here is a sort of depiction of the architecture that Ludwig takes on in order to make these integrations possible. So with Ludwig, you can get Ray, Dask, and Horovod to interact with one another in order to do dataset partitioning, data set sharding, pipeline data loading, and distributed data parallel training very easily. In fact, a large number of OSS users leverage these integrations heavily. Most deploy Ray on Kubernetes clusters via KubeRay and train models via Ludwig on top. That said, getting the setup and managing it still requires significant cloud infrastructure investment. So if you're not interested in putting in that time, we've already done a lot of that work for you at Predibase. So Predibase is sort of this application where we take a declarative system like Ludwig and integrate it into an end-to-end declarative ML platform designed to support modern enterprise across the entire ML lifecycle. So we start with Ludwig at the core to provide declarative model training and build on those capabilities in 4 distinct ways. We provide a series of data connectors to make it easy and fast to connect to any structured and unstructured data source like S3, Azure Blob Storage, GCP, Snowflake, and Databricks, among others. We also provide a fully featured experiment tracking platform through a Git-like model repository, which I will be showing off a little bit later, which allows you to track changes across models over time, analyze performance, and compare models across experiments. And finally, after you've trained your models, we also offer a 3-pronged operationalization story, which means you can deploy your models on the platform for real-time inference or batch inference, or export your model into a Ludwig model or some compiled model such as TorchScript. Regardless of what you do, your model will be capable of end-to-end inference from pre-processing to model inference to post-processing. And finally, all of this is hosted on a managed modern cloud stack using best-in-class infrastructure. Our compute layer intelligently scales up and down based on your workloads, ensuring that you never have to think about infrastructure as you realize value from your data. So with all of this in mind, I'd like to take some time to go through a demo. All right. So today we're going to do a demo using the TwitterBots dataset. So here I have VS Code open. I have nothing in this folder except for this empty YAML file and the TwitterBots CSV, which I have open here in Pages. Now you can imagine yourself in my shoes as a software engineer who is, for the first time, attempting to get value from this data. So TwitterBots is a content moderation data set, which essentially takes accounts and their metadata and then labels them as either human or bot. So you can see here that one of the columns has bot or human as its types. And then we also see that we have a bunch of metadata having to do with the account itself. So we have the description, the bio of the account. We have the number of followers, the number of favorites, things along these lines. So what we can do to get started with this is actually just start to write our config as we had in the demo. So doing such a thing would be relatively straightforward. We can actually just start picking out columns and then determining whether or not we want to use them. So I think personally that a bot is somebody who is likely to have a default profile image. So I'm going to go ahead and add that as a feature. And when I'm adding these feature types, we can actually just reference directly Ludwig's extensive documentation. So if we go to the Ludwig AI website, we can go into something like the configuration page and take a look at the various input features that we have available to us. And as I was looking at this, I see that it looks like a true-false column, so I'm actually going to use the binary feature. And so I'm going to go ahead and fill that in. And then maybe for the next one, we can take a look here. We see something like followers count. I think that's a good signal that someone is a bot. They don't have a lot of followers. And we can go ahead and fill this out. Since this is a demo, I'll save you the trouble of watching me fill out every single column here and just go ahead and copy and paste this in. And what we have here is the simplest config you can imagine for this sort of data set. We're actually not going to use the text description at this moment, but we're going to go ahead and train our first baseline using these features alone, and we're going to do it directly from my laptop. So here I'm going to go ahead and set up my environment. I have not written a single line of Python yet, but I can go ahead and run the Ludwig experiment from here directly. And Ludwig takes a dataset path, the config, and we're good to go. So I'm going to go ahead and start this. And it should train relatively quickly because this is right now just tabular data. I've not included any unstructured data. So I have here binary and number features. And, oh, what did I do? Oh, I see. Yes. One of the arguments, okay. Oh, I see. You know how it goes with demos. Okay. Uh-oh. Let's see. All right. So I am not sure if I'm going to be able to get this to train, but that's all right. Because the next thing I'd like to show you essentially is that we can take the model that we would otherwise train and then see that the ROC AUC is going to be 0.78. So when we train this model, man, I would really like this to work, but I don't know if we're going to be able to do it. Yeah, very weird. Experiment. Okay, so I guess what we'll do is actually just quickly hop over to Predibase because that's where the demo was going to go anyway. So after we've trained our model, this is sort of what we can expect from Ludwig, which is that we can get the baseline that we've trained and take a look at its performance. So as I was saying, we were going to get an AUROC of 0.78, and here we get a similar baseline, which gets 0.77, and we're able to get that value directly from the config just by training this using this very simple YAML file. Now, after we've generated this model, we can actually go ahead and iterate on the Predibase platform ourselves. And so one thing I'd really like to do is actually use the unstructured data in our data set. So we have all of this tabular data, but we also have this description column that we might want to use. So what I can do from the Predibase platform is click New Model from One. And what will happen is we're sort of put onto this model builder flow, right? And in Predibase, in contrast to Ludwig, we actually have a lot of really strong experiment tracking capabilities. So here we can write a description, so include text feature. The next thing we can do is look at the connections. So here I've uploaded the file TwitterBots, but we can also use data sets from BigQuery, Postgres, or S3. And then after that, let's actually leave the target and the model type alone, even though we could use a tree model in the tabular sense. And then we can take a look at the data sets, the columns that we had for this data set here. So we do have the binary and number features already selected. And let's confirm that the column that we want is description. So here we have a data set preview. I, as an engineer, find this super useful because while I could download the CSV onto my own computer, it's actually really nice to see it in this case, particularly if I'm connecting from a remote file system like S3. So here we have the description column. Let's go ahead and select that as active, and now we're going to go through the model builder flow. So here we are again. Here's our config. You notice that text has been added to the config that we have. We can actually make edits directly here, but I'd like to show off a little bit of the support that Predibase will give you in order to do the model editing work. So there are sort of two views in Predibase through which you can make changes. You can make changes directly to the architecture via this GUI. So if we wanted to make changes to our text preprocessing, we could click on the text and make changes here. Notice how there is extensive documentation and suggestions on how to move forward with your machine learning model directly baked into the Predibase platform, which means that modeling decisions become much easier than they would otherwise be out in the wild. And also we do have this sort of drop-down-esque model builder flow, which allows you to sort of go through the config, but in a visual fashion, right? So the thing I'd actually like to add here is regularization. Since we're adding this deep learning encoder, this text encoder, I have a hunch that this is going to overfit. And so one way I could do this and add regularization is actually through something like hyperopt. So Predibase offers, and Ludwig offer, hyperparameter optimization right out of the box. So we can train multiple models in parallel based on our desired sort of behavior. So if I thought I needed to explore the space of regularization lambdas and regularization strength to prevent overfitting, I could actually go ahead and start a hyperopt experiment right here, right out of the box. If you look at the config, this is reflected here, and we actually will generate 3 models in parallel, each of which have configs specified with that particular regularization right there. But in this case, I'm not going to do that. as part of the demo, what I would actually like to do is just train a model that uses a fixed lambda, so we only get one model back. So making the change in the parameters window, I can actually get that value back in the config. Now, initially, the way that I was intending on doing this was once we moved from Ludwig, which trained on my laptop, over to Predibase, the intent was that I would be adding an unstructured piece of data, which would require a GPU for me to train. Tabular models train fine on CPU, but deep learning models really require that GPU integration. And so far, I haven't done anything to make that happen. And the reason why is because Predibase has engine right-sizing capabilities baked into the platform. And the way it's able to do that is actually quite cool. It uses information about your data set, and it does static analysis on your model config. So this is one thing that makes Declarative ML really special, is that you have your full specification of your models baked directly into this YAML file. So we're able to inspect that and make decisions about what to do next just by looking at the config, which is not necessarily true in an imperative world where you have a bunch of code and it's very unclear what it does until it runs, right? So if I were to remove description, the description field, then we clicked over the compute tab, we'd see that Predibase has selected AWS M5 instance with 0 GPUs for training. But if we were to add it back in, like so, we would see that the compute tab has changed and has now updated it to be an instance using a GPU. So we never have to think about infrastructure in order to train Predibase models. We can just go ahead and do it, and Predibase will manage the cost and ensure that we get a balance of training efficiency and also cost savings. That said, you can still always control how much compute you're using. We do allow for you to do that using engines and using training workers. So if you want to really bump up that parallelism for distributed data parallel training, you can do so by increasing the training workers. All right, so if I were to actually train this model, I would click train, but because this is a demo, I'm going to go ahead and go into this already trained model that used L2 regularization. So from here, you can see that our ROC AUC was 0.81, so we do get a bump in performance. And we can also start to analyze the learning curves of our model. Here we can see that the model still overfit just a little bit. If you analyze the metrics here, we see that the ROC for training is 0.88, which is much better than test and val. But that means that we have some iterations to go. So at a high level, we can use the model version page that we have here to assess performance, but actually go much deeper. So as I mentioned, we have static analysis for model config, which means that we can actually determine what would be the most useful for you as an engineer / data scientist to use in order to determine whether or not your model is worth putting into production. So if we go into the config, we see that our account type was binary, which means that Predibase has decided that the most useful visualizations that you could have for this are things like the confusion matrix. So here we can see how our model was made predictions, the ROC curve for threshold selection, precision recall curve for a similar thing. And the last thing, which I'm very excited about, is that we've actually offer a method for opening the black box that is machine learning through model explanation and feature importance analysis. So here we can go into this tab and start to analyze the feature importance. So here are all the features that we've given to our model. And we see that description was actually a super useful feature for our model for determining humor in a bot. And we can actually go and break that down even further in the text explanations. So from this tab, you can see what words exactly were being used to tip off our model in terms of whether or not the account was a bot or a human. Great. So now that we've seen sort of what the model version page looks like, there is one more thing that I wanted to show you before we move forward, which is the model repository. So the model repository is where all of the models that I've trained for this demo are collected. So I've hidden the archived models, but you can see here that I went through a lot of iteration in order to get to a model I was proud of for presentation. And we can actually see the thought process that I went through in order to train these models using the model lineage tab. So from here, you can see that the main through line gets us to the L2 regularization model version, but that I also tried a bunch of other things. So this middle line actually was me trying the image feature in the TwitterBots dataset to see if I liked that. Now, one thing we can do, because we have a declarative system, is make comparisons with our models and be confident that those comparisons are exactly what has changed in order to get better model performance. So here, if we compare our baseline, which is what I showed you earlier, with the final version, we can see that what we added was description and what we added was regularization. Now, this is different than the imperative sort of paradigm, because in the imperative world, you would be comparing commit hashes, you would be comparing configs, you would be going into those commit hashes and looking at how the code has changed. But here, because we have this interface, we're able to be confident about what changes were made and how that affected our model architecture. So with that in mind, I'd like to actually take one step forward and take our trophy model, the model with the best ROC AUC, and talk a little bit about how we would get this out into production. So in Predibase, there are three options. The three options are downloading the model onto your machine and then using that artifact to then operationalize. So here we can download it into Ludwig, or we can use a compiled format like TorchScript or something else like NVIDIA Triton or Neuropod. We can also send it off to be hosted on an endpoint for real-time serving. So here we can specify a deployment name, the kind of compute we want the deployment to live on, and then what is returned to us when I click this deploy button is a URL that we can then ping with data in order to get predictions. But between these two options, there's actually a third option that I'd like to quickly show off, which is our query functionality. So Predibase allows us to not only train models, but also inspect the data associated with the models and even use the models within a platform using our SQL-like extension, the predictive query language, which essentially allows you to blend SQL with predictive analyses that leverage your models. And so I can write a statement like select star from TwitterBots, limit 10. Once I've selected the correct data source, I can run this and expect to get back that same information that I was seeing in the dataset preview, which is the TwitterBots dataset itself. So that's nothing special, that's just SQL. But what we also can do is add a series of custom clauses, such as predict account type given select star from TwitterBots. And now we are going to use the model that we just trained in order to get predictions on the data set without ever having to take the model off the platform and without ever having to write any infrastructure code at all. So actually what I'm going to do is get explanations as well so that I can get that auditability. And if I were to run this, I would get back a table of the data set joined with the model's predictions. So that's actually exactly what I've done here. What we see here is the table, but we also see the model's predictions. So here we see bot human human, and we also have the explanations. And so we can click into this and see why exactly the model made a prediction for this particular sample. And we can do so both at the feature level, but also at the text level. Now, one thing I wanted to make sure to mention is that this doesn't have to be on our data that we just trained, right? We can do this sort of just for confirming that it works, but what we really can do is upload new data in order to do batch inference over time. So if maybe a month from now we have new Twitter bot information, we can just connect that data source using the dataset connectors. We probably wouldn't be uploading a file. Maybe we would be doing some sort of scheduled upload through Snowflake or something along those lines. But really, you can start to generate those predictive analyses and derive value from your data very quickly using Predibase. So that pretty much wraps up my demo. I hope that that was helpful for you all. I will now switch back over to the presentation, land it on our final slide, and take questions. So thank you for watching the demo. I know we didn't get to using Ludwig in the CLI, but I hope that was useful for you all.
Thanks, Jeff. And Dev, a number of questions have come in throughout the presentation. So let's just kind of rapid fire, get into appreciate the awesome demo and presentation.